Magnetite is a mineral, one of the three common naturally occurring iron oxides and a member of the spinel group. Magnetite is the most magnetic of all the naturally occurring minerals on Earth. Naturally magnetized pieces of magnetite, called lodestone, will attract small pieces of iron, and this was how ancient people first noticed the property of magnetism. Small grains of magnetite occur in almost all igneous and metamorphic rocks. It is black or brownish-black with a metallic luster, has a Mohs hardness of 5/6 and a black streak. The chemical IUPAC name is iron, II3, oxide, and the common chemical name is ferrous-ferric oxide. Properties: lodestones were used as an early form of magnetic compass. Magnetite typically carries the dominant magnetic signature in rocks, and so it has been a critical tool in paleomagnetism, a science important in understanding plate tectonics and as historic data for magnetohydrodynamics and other scientific fields. The relationships between magnetite and other iron-rich oxide minerals such as ilmenite, hematite, and ulvaspinel have been much studied. The reactions between these minerals and oxygen influence how and when magnetite preserves a record of the Earth's magnetic field. Magnetite has been very important in understanding the conditions under which rocks form. Magnetite reacts with oxygen to produce hematite, and the mineral pair forms a buffer that can control oxygen fugacity. Commonly, igneous rocks contain grains of two solid solutions, one of magnetite and ulvaspinel and the other of ilmenite and hematite. Compositions of the mineral pairs are used to calculate how oxidizing was the magma. A range of oxidizing conditions are found in magmas, and the oxidation state helps to determine how the magmas might evolve by fractional crystallization. Magnetite also occurs in many sedimentary rocks, including banded iron formations. In many igneous rocks, magnetite-rich and ilmenite-rich grains occur that precipitated together in magma. Magnetite also is produced from peridotites and donites by serpentinization. The Curie temperature of magnetite is 858 K. Distribution of deposits. Magnetite is sometimes found in large quantities in beach sand. Such black sands are found in various places, such as California and the west coast of the North Island of New Zealand. The magnetite is carried to the beach via rivers from erosion and is concentrated via wave action and currents. Huge deposits have been found in banded iron formations. These sedimentary rocks have been used to infer changes in the oxygen content of the atmosphere of the Earth. Large deposits of magnetite are also found in the Atacama region of Chile, Valentines region of Uruguay, Kiruna, Sweden, the Pilbara, Midwest and Northern Goldfields regions in Western Australia, New South Wales in the Talawang region, and in the Adirondack region of New York in the United States. Kiryat Ejgil, the highest mountain of Mauritania, is made entirely of the mineral. Deposits are also found in Norway, Germany, Italy, Switzerland, South Africa, India, Indonesia, Mexico, and in Oregon, New Jersey, Pennsylvania, North Carolina, Virginia, New Mexico, Utah, and Colorado in the United States. In 2005, an exploration company, Cardero Resources, discovered a vast deposit of magnetite-bearing sand dunes in Peru. The dune field covers 250 square kilometers, with the highest dune at over 2,000 meters above the desert floor. The sand contains 10% magnetite. Transformation of ferrous hydroxide into magnetite. Under anaerobic conditions, the ferrous hydroxide II can be oxidized by the protons of water to form magnetite and molecular hydrogen. This process is described by the Shakur reaction, 3Fe, OH, 2Fe3O4 plus H2 plus 2 hours 2O, ferrous hydroxide and magnetite plus hydrogen plus water. The well-crystallized magnetite is thermodynamically more stable than the ferrous hydroxide II. Biological occurrences. Biomagnetism is usually related to the presence of biogenic crystals of magnetite, which occur widely in organisms. These organisms range from bacteria to animals, where these crystals are found in the brain. These crystals are involved in magnetoreception, the ability to sense the polarity or the inclination of the Earth's magnetic field, and aid in navigation. Chitons have teeth made of magnetite on their radula. Synthetic magnetite. Magnetite can be prepared in the laboratory as a ferrofluid in the Massart method by mixing iron, 2, chloride and iron, 3, chloride in the presence of sodium hydroxide. Magnetite can also be prepared by the chemical co-precipitation in presence of ammonia, which consists in a mixture of a solution 0.1 m of FeCl3 a 6 hours duo and FeCl2 a 4 hours duo with mechanic agitation of about 2000 rpms. The molar ratio of FeCl3, FeCl2 can be 2:1. Heating this solution at 70 AA degrees Celsius, and immediately the speed is elevated to 7500 rpms and adding quickly a solution of NH4OH, immediately a dark precipitate will be formed, which consists of nanoparticles of magnetite. In both cases, the precipitation reaction rely on a quick transformation of acidic hydrolyzed iron ions into the spinel iron oxide structure, by hydrolysis at elevated pH values. Considerable efforts has been devoted towards controlling the particle formation process of magnetite nanoparticles due to the challenging and complex chemistry reactions involved in the phase transformations prior to the formation of the magnetite spinel structure. Magnetite particles are of interest in bioscience applications such as in magnetic resonance imaging since iron oxide magnetite nanoparticles represent a non-toxic alternative to currently employed gadolinium-based contrast agents. However, due to lack of control over the specific transformations involved in the formation of the particles, truly superparamagnetic particles have not yet been prepared from magnetite. That is magnetite nanoparticles that completely lose their permanent magnetic characteristic in the absence of an external magnetic field. The smallest values currently reported for nanosized magnetite particles is Hc equals 8.5 AMR1, whereas the largest reported magnetization value is 87 m2 Ga1 for synthetic magnetite. Applications: magnetic recording. Magnetic iron oxides are often used in magnetic storage, for example in the magnetic layer of hard disks, floppy disks and cassette tapes. These consist of a thin sheet of plastic material, with embedded magnetic particles. The particles can be magnetized to represent binary or analog data. Magnetic ink character recognition also uses magnetic particles suspended in an ink which can be read by special scanning hardware. Most newly generated information, such as text, photographs, and audio-visual recordings, is now stored in magnetic media, and much of the world's legacy of information in other media has been transcribed to magnetic form, because it is cheap, compact, and computer-accessible. Catalysis. Magnetite is the catalyst for the industrial synthesis of ammonia. As a sorbent, magnetite powder efficiently removes arsenic, 3, and arsenic, B, from water, the efficiency of which increases 200 times when the magnetite particle size decreases from 300 to 12 nm. Arsenic-contaminated drinking water is a major problem around the world, which can be solved using magnetite as a sorbent. Because of his stability at high temperatures, it is used for coating industrial water tube steam boilers. The magnetite layer is formed after a chemical treatment. Gallery of magnetite mineral specimens. See also, bluing, a process in which steel is partially protected against rust by a layer of magnetite, Buena Vista iron ore district, corrosion product, ferrite, greigite, magamite, magnesia, magnetotactic bacteria, mill scale, mineral redox buffer, references. Further reading: Lauenstam, Heinz A. Weiner, Stephen. On Biomineralization. USA, Oxford University Press. ISBN A0-19-504977-2. Chang, Shibin Robin. Kirschvink, Joseph Lin. Magnetofossils, the magnetization of sediments, and the evolution of magnetite biomineralization. Annual Review of Earth and Planetary Sciences 17, 169 195. Bibcode, 1989 AREPS 17169 C doi, 10.1146/ANNUREV. 17.050189.001125. External links, Mineral Galleries, Biomagnetics, History of Magnetite Mining in the NJ Highlands, Magnetite mining in New Zealand accessed March 25, 2009, mineral survey of Santa Cruz County, black sand, Peruvian sand dunes.